Hi folks, what we're going to look at now is what we call solving an inequality. All right, so what's an inequality? Let's take a look at a couple of examples. Here are a couple examples of inequalities, and I hope that you notice that these look a lot like equations or equalities. All right, in fact, they look a lot like, in this case here, linear equations. So let's take a look at what an inequality means. So what we're doing when we want to solve an inequality is we want to find the x values such that 4x minus 15 is going to be greater than or equal to 1. Now, I'm hoping that you can see that I said the x values because there's likely to be many x values for which 4 times that value minus 15 is going to be greater than or equal to 1. In fact, there's probably going to be infinitely many solutions. And similarly here, we want to find what are the x values such that negative 2 times that x value plus 3 is strictly less than 7. Okay? So, of course, when we see something that looks so similar to something that's familiar, namely linear equations, hopefully we can apply some of the same methods that we used for linear equations for linear inequalities. So let's see if it makes sense to do that. All right, so let's take the same expression but make it an equation. So if we have 4x minus 15 is equal to 1, and the way in which we were able to solve a linear equation was to just use opposite operations to isolate our variable. So here we could add 15 to both sides, the idea being that if I add the same thing to both sides of the equation, it'll still keep both sides equal. So 16, and then similarly here, if I divide the left-hand side by the same amount that I divide the right-hand side, the equality will hold. So x equals 4. So that means that if I replace x by 4, 4 times 4 is 16 minus 15 is equal to 1. It solves this equation. Okay? So does it make sense to use opposite operations to solve an inequality? Okay, so let's go back to some basics here. Let's take a really easy inequality. I think we can all agree that 2 is less than or equal to 3. Just 2 is less than 3. I'll use that one there. So let's see if it makes sense to do the same thing, that if I apply one operation to the left and the same operation to the right, that it should still keep the inequality correct. Okay, so let's start by adding 3 to both sides. So let's say I do 2 plus 3. Is that still less than 3 plus 3? So let's see. Here we've got 2 plus 3 is 5. Here we've got 3 plus 3 is 6. And indeed, the inequality holds. Okay, 5 is less than 6. Okay, let's do the same thing with subtraction. Let's subtract 3 from both sides. So 2 minus 3, is that still less than 3 minus 3? And here we have negative 1, here we have 0, and indeed this is less than 0. So even though the absolute value is bigger, remember on a number line, that's 0, that's negative 1, okay? You're worth more if you owe $0 than if you owe $1, okay? So let's keep going. Let's do 2 times 3, and 3 times 3, is that inequality still holding? Well, 2 times 3 is 6, makes it bigger, but of course 3 times 3, even bigger than that. So yes, 6 is still less than 9. And lastly, let's divide. So 2 divided by 3, is that still less than 3 divided by 3? Okay, so here we have 2/3, here we have 1, and of course 2/3 is indeed less than 1. Okay, so it seems to make sense that if I perform one operation on the left and then that same operation on the right, the inequality is still going to hold. Okay, so let's go back to our examples and see what happens. All right, so let's take a look here at 4x minus 15. So I'm going to do the same things as before. I'm going to add 15 to both sides. So it gives me 4x greater than or equal to 16. And then divide 4 to both sides. X is going to be greater than or equal to 4. So what this is telling me is that for any value that's greater than or equal to 4, if I stick it back into my original inequality, it should hold. So let's take 4. Well, we kind of know that's going to work because 4 times 4 is 16 minus 15. Is that greater than or equal to 1? Yeah, it is because it's equal to. So that's included. Let's pick 5. 4 times 5 is 20 minus 15. is still going to be greater than or equal to 1. Take 10. 4 times 10 is 40 minus 15. That's going to be greater than or equal to 1. But if I try to take something that's not in this set, let's say I take 3. 4 times 3 is 12 minus 15 is negative 3. That's not greater than or equal to 1. All right. And if I take anything else that's less than 4, I'm going to see that the inequality won't hold. So that means these are all the x values that satisfy that inequality. So let's do this one here. Same thing, negative 2x. I'm going to subtract 3 from both sides. So 7 minus 3 is 4. Then divide both sides by negative 2. So 4 over negative 2 is negative 2. And so this tells me that for any value less than negative 2, the inequality should hold. So let's test that out here. So let's say I take negative 3, so negative 2 times negative 3 plus 3. So negative 2 times negative 3 is 6, plus 3 is 9. Oh, that's a problem, because 9 is not less than 7. So we've got a problem here. Let's say we take something bigger than negative 2. According to this, it shouldn't work. But if I replace, say, x by 0, negative 2 times 0 plus 3 is 3 is less than 7. So clearly there's a bit of an issue here. Okay, it seemed to work with all these operations. Okay, but the one thing I noticed that's different in this scenario here is that notice how my coefficient of x was negative. And I think that might cause a bit of an issue. Because let's say I start again with 2 is less than 3. Let's multiply both sides by negative 3. So 2 times negative 3 and 3 times negative 3. Is that inequality still going to hold, or what do we have? We have 2 times negative 3 is negative 6. 3 times negative 3 is negative 9. That is not correct. In fact, it's the other way around. Negative 6 is greater than negative 9. Again, if we go back to our number line, there's negative 6, there's negative 9. You're worth more money if you only owe $6 than if you owe $9. Okay? So this seems to tell us that there's an extra little subtlety when solving linear inequalities. That if we multiply or divide by a negative number, let's check division here. Let's say let's take something easy. I have 10 is less than 12. We can all agree on that. But let's divide both sides by negative 2. This gives me negative 5. This gives me negative 6. Negative 5 is no longer less than negative 6. It's greater than negative 6. All right? So we see that multiplying or dividing by the negative, okay, results in having to switch to flip the inequality in the other direction. So if I go back to my example here and I apply this new knowledge, so that's gone. Let's apply this new idea here that we have to switch the inequality when we're multiplying or dividing by a negative number. And let's see if we get something that's reasonable. So this gives me negative 2x is less than 7 minus 3 is 4. So we determined addition and subtraction. There was no issues. So x now, when I divide both sides by negative 2, is actually going to be greater than negative 2. And this seems to fit what we checked before. That if I take something outside of this range of values, so I took negative 3, the inequality doesn't hold. But if I take something strictly bigger than negative 2, like 0, we had that the inequality does hold. So solving linear equations, good news, it's almost exactly, solving linear inequalities is almost exactly like solving linear equations, okay? But there is that extra little subtlety involved. All right? So what you should be doing now, in principle, is turning off the video and doing these on your own. But I'll pause for a second, and then you can come back and check your answers. Okay, so we're back. So I'm just going to quickly go through these here. I got a little something to say on that last one. So here I'm just going to solve with what I had by opposite operations. So here 15 plus 5 is 20. So x is less than 20 over 8. Of course, I'm not going to leave it that way. Okay, so divide numerator and denominator by 4, and we have 5 over 2. All right, so there's our answer. But notice how it's asking us to give the final answer in set or interval notation. Okay, so this is a good opportunity to practice these here. So if I were to write this in set notation, what would be x can be any real number such that x is less than 5 over 2, so using the inequality symbols. Or if it has to be less than 5 over 2, I know it's going to go from negative infinity to 5 over 2, not inclusive because it's not less than or equal to, it's just less than. This one here, we see that we've got x's on both sides of the inequality. We're just going to do the same thing as we would when we had x's on both sides of an equation. I'm going to bring everything, all those variable terms to one side and the numerical ones to the other. Now notice here, I could bring the minus 3x to the other side, do plus 3x, and that takes away the negative coefficient. But just so that we can practice flipping the inequality, let's do it the other way around. So I have negative 3x, the x comes to the other side, minus x, greater than or equal to 7 minus 5. So here we have negative 4x greater than or equal to 2. So notice here, nothing changed because it was just additions and subtractions. Whereas now, when I divide both sides by that negative number, I'm going to switch the inequality to less than or equal to. So x is less than or equal to negative 1/2. Okay, and you can check here if you want whether this indeed makes sense. All right. So here, x is less than or equal to negative 1/2. So again, we're going to be going negative infinity to negative and a half, except now we're going to be including the negative 1/2. And of course, in set notation, x can be any real number such that x is less than or equal to negative 1/2. Okay. Now this is an interesting one because here, 9 minus 2x doesn't just have to be less than or equal to 15, or greater than or equal to negative 5, it has to satisfy both of these conditions. And notice how we took those two inequalities. So we took the inequality 9 minus 2x less than or equal to 15 and 9 minus 2x greater than or equal to negative 5, and we combined them to write a single inequality. So this only works when your expression has to be between two numbers. And obviously the one on this side has to be less than the one on the other side, given the inequalities. Okay? But since this really represents two separate inequalities, I can just solve it in the exact same way. I'm going to do the same thing as before. I know that I would be subtracting 9 from both sides here and there. So I'm going to do the same thing here. I'm just going to subtract 9 from both sides of the equation. So 15 minus 9 and negative 5 minus 9. Oops, 2x. So negative 2x is less than or equal to, well, 15 minus 9 is 6. And it's also greater than or equal to, well, negative 5 minus 9 is going to be negative 14. And now similarly, I'm going to divide both sides of this inequality and that inequality by negative 2. But of course, I need to be careful that because I'm dividing by a negative number, I'm going to have to flip the inequality on this one here and on the other. So here, this is going to be 7. Okay. So while this is not an incorrect way of writing it, usually we like the whole left to right thing. So I'm just going to rewrite this now as negative 3. Of course, now that's going to be less than or equal to x, and that's going to be less than or equal to 7. This is the preferred way of writing it out. And of course, if I want to now write it in set notation, x is an element of R such that negative 3 is less than or equal to x is less than or equal to 7. Or, much simpler, I can use interval notation, so 3 and 7. And since they're both equal to, I'm going to include. So that means all numbers between 3 and 7, including 3 and 7, satisfy these two inequalities. All right, that's it for now.